Good morning, everybody. We're going to continue on with chapter 6, which again, as I said, is kind of a hardy chapter. Last time we talked about and were introduced to the mole and how we can go from atoms or molecules into moles. And then we also went from moles into grams using the molar mass. And the molar mass isn't something you have to have memorized, it's something that you can get off the periodic chart. And I believe we left off, let me share my screen with y'all. We left off talking about calculating the molar mass for molecules. So it's a little extra work in that you have to sum up all the individual elements multiplied by however many of them you have to get the total molar mass. I'll go back here. We had a flow chart as well, which I hope my daughter didn't erase. She was on my computer. There it is. Okay. So excuse my horrid handwriting, but what we've got here are two tracks or two paths. The top path here has moles of the element in the center, and we can get from moles of an element into number of atoms using Avogadro's number. So that's the 6.022 times 10 to the 23rd. We can go from moles of an element into grams using molar mass. Now, if we happen to have a compound, moles of compound again will sit in the middle. Moles of compound, we can go to molecules, again, using Avogadro's number. And then we can go from moles of compound into grams of compound using the molar mass of the compound that you calculate. And we will talk in a minute about how to get between these two here, but let's do a problem where we okay, so let's say that we're given the number of molecules of a material. So I'm going to give you that we have 4.07 times 10 to the 24th FeOH2 molecules. Okay. I want you to find how many grams of FeOH2 this is. So how much does this thing weigh in, like, real life? I'm let me scroll this down just a little bit. Okay, so that we can see what we have going on here. So we're talking about a molecule. We'll ditch the element thing for now. You're given number of molecules. So you're going to start over here. I want y'all to end over here. So I'll give you 5 minutes to set that up. You will need to calculate the molar mass of this thing. If you have any questions while you're working on it, anyone wasn't here last time and has a quick question, either throw it in the chat or you can just turn your mic off and ask me. So back. So in this one, we're going to need to do 2 steps. The first step is to get from molecules, move this up. We need to get from molecules into moles and then from moles into grams. There's no direct way to go from molecules to grams. It'll always be a 2-stepper if that's where you are on the flow chart. So we start with our given information, and we know that we have 4.07 times 10 to the 24th FeOH2 molecules. So we need to convert this into moles, and we know that for every 1 mole of FeOH2, it will hold or yield 6.022 times 10 to the 23rd FeOH2 molecules. Okay, this is Avogadro's number, Avo's number for this step. The next step is to go from moles into grams. So 1 mole of FeOH2, and we need to figure out how many grams that is. So that's where you calculate its molar mass. So we're going to take the mass of 1 iron and combine it with 2 oxygens and 2 hydrogens. And so we should have something like 89.86 grams of the FeOH2. I'd start to get in the habit of writing, don't just write gram, mole, put whatever the compound is that you're dealing with, because when we get a little bit deeper into this test section here, we're going to be having moles of one compound, and then we're going to have moles of another compound, and we don't want to get our moles mixed up. So molecules of the compound cancel, moles of the compound cancel, and we'll be left with just grams. And in this case, we've got, let me run it through my calculator really quick. So 4.07 EE24 divided by our 6.022 EE23 times 89.86. I got 607, and I'm going to stop there because of sig figs, grams, and specifically grams of FeOH2. Does that make sense, what we did there? You guys like that? At least the setup. You don't like doing it, but it at least makes sense. It doesn't say something. We'll do a problem going the other direction. So I'm going to give you grams, and I want to know molecules. Won't give you quite as much time on this one. Let's say we've got, given that we have 28.7 grams of water. Find how many water molecules there are. How many water molecules are contained in 28.7 grams of water? So we're at 8:21. I'll give you 4 or 5 minutes, and then we'll come back. Okay, so in this instance, we're going from grams, then we'll go to moles, and then from moles we'll go into molecules. So in order to go from grams to moles, and we need to know that water is H2O because the name itself doesn't preserve the formula. We know 1 mole of water weighs roughly 18.02 grams. Water. Those will cancel. And then for every 1 mole of water, it will yield 6.022 times 10 to the 23rd H2O molecules. And what we get is I have 9.59 times 10 to the 23rd H2O molecules. Make that a little clearer. Okay. So again, I don't think about it in the sense of, oh, if I'm going from this to this, I have to divide, or if I'm going from this to this, I have to multiply. I just set it up in my dimensional analysis so the units cancel and let it tell me if I'm going this way or if I'm going this way, right? Because if we're going in this direction, we divide by Avogadro's number and multiply by molar mass. In this case, we divide by molar mass and multiply by Avogadro's, but I don't preserve that in my opinion, useless information. If I know what my flow chart is, then I can just, manipulate the conversion factors from there. So not the last, but the next thing I want to talk about are 3-leaf clovers, which is insane. Where did that come from? But this is how we can conceptualize a compound in relationship to its individual elements. So here we have 1 clover, okay? Every 1 clover contains 3 leaves. So this in and of itself is a conversion factor. So you can have 3 of something contained within 1 of something else, if that 1 of something else is sort of a bigger thing, right? So the clover itself is large. The 3 leaves are smaller. That's why we can have 3 of them. So if we were going to do a conversion factor like this says, how many leaves are on 14 clovers? We'd start with our clovers. So we have 14 clovers. And we know that for every 1 clover, we get 3 leaves. Or we have a total of 42 leaves. So a couple other things that we can have a conversion factor for in real life. A spider. So 1 spider has 8 legs. 1 chair has 4 legs. Well, 1 water molecule has 2 hydrogen atoms because it's H2O. Another way to look at that, if we're looking at, say, CO2, so if we have carbon dioxide, that's saying that for every 1 carbon dioxide, we get 2 oxygen atoms, right? 2 oxygen atoms for every 1 CO2 molecule. Again, you can have 2 of something within 1 of something larger. Similarly, we could have 2 dozen oxygen atoms for every 1 dozen CO2 molecules. And since the mole is our dozen on steroids, we can have 2 moles of oxygen within every 1 mole of CO2. So super nifty because every single one of these formulas, if written correctly, has a built-in relationship between a mole of the molecule and individual moles of the element. So we could jump from the amount of CO2 to the amount of oxygen or the amount of carbon because we know the relationship. So let me do another one and then I'll have you guys do one. No, we don't want that. So So what was the last, we had water, we did water, but let's not do water. Oh, FeOH2, right? FeOH2. So for one FeOH2 molecule, we have one Fe atom, just one, okay? We also have two oxygen atoms, because that 2 gets distributed to both things within the parentheses. And we also have 2 hydrogen atoms. The little colons here are just saying that these 2 things are related to each other. So if I want to make this specific molecule, I would need 1 iron for every 2 oxygens, or for every 2 oxygens, we'd need 2 hydrogens. I can just as easily change molecule atoms as a relationship of moles. So 1 mole of FeOH2 has 1 mole of iron in it. It also has 2 moles of oxygen, and it has 2 moles of hydrogen. So built into that nifty formula. So I want you to do one of these. Let me give you a formula that's a little bit prickly. So let's say we've got 1 mole of Ca3PO4 This thing here is calcium phosphate. I want you to tell me how many moles of each of the individual elements you get. Okay, so for every 1 mole of this, how many moles of calcium are you going to get? How many moles of phosphorus are you going to get? And how many moles of oxygen are you going to get, or do you need in order to make the correct formula? So just a minute for that. Okay, so 1 mole of calcium phosphate will yield 3 moles of calcium, right? Or you need 3 moles of calcium, or 3 moles of calcium are contained within one of those molecules, or 1 mole of that. We also have 2 moles of phosphorus, and we have 8 moles of oxygen. The 2 gets distributed to the 4 oxygen, so we multiply those, and then it gets distributed to the P as well. So now we've got a built-in relationship between these. So let's use this here. What if I say that we have 21.2 moles of Ca3PO4 and I want you to find moles of oxygen. So you have a relationship here. 1 mole of this will yield 8 moles of this. We're not talking about these things, so we can sort of ignore them for this problem and just look at this relationship here. So this guy in relationship to this guy. So go ahead and try that out. So setup wise, we start with our given. Just ignore that. Okay, so we have 21 point. Come on. My pen is not working for me today. 2 moles of Ca3PO4. 2. And I want to figure out how many moles of oxygen this is. Well, the relationship is that for every 1 mole of the molecule, and you always put the 1 mole with the compound. All right, so for 1 mole of this, it should yield 8 moles of oxygen. We've got that here. I can also see it right here. We've got that 21.2, and we're just going to multiply it by 8, and we end up with, well, it's 169.6, and I would round that to 2 sig figs, so it would be 170 moles of oxygen. So there's 170 moles of oxygen contained within 21.2 moles of calcium phosphate. If you're thinking, well, how can you have 170 of something and 21 of something? Well, this is 170 moles of oxygen. Remember, oxygen only weighs 16 grams. This compound is much, much heavier. Okay. So now we've got a nifty way. We're going to go back up to that flow chart, and we have a way of going from moles of an element to moles of a compound, or vice versa. So let's fill in here a little arrow. And in order to do this, we use the formula, or formula subscripts. We can also use formula subscripts to get between atoms, number of atoms, and number of molecules. That's what we did right here, right? A molecule of this contains this many atoms of each. So we can also put formula subscript there. Now let's go over to this one here, grams of element to grams of compound. Can I put formula subscript there? No, definitely not. Because this relationship in a formula is a relationship between molecules and atoms. It's a relationship between moles. It's not a relationship between mass. So I'm not saying 1 gram of this is equivalent to 1 gram of this and 2 grams of this. That is not true. So put like an X here, or something to remind you that there's no direct path, no direct path. So if you're given grams of a compound, and you want to figure out grams of an individual element, you don't get to go this way. You have to go here to here to here. Grams to moles to moles to grams. Grams of compound, moles of element, grams of element. You could, if you wanted to, go grams to moles to molecules to atoms to moles to grams. I wouldn't do that though. I would just do the shortest path. So let's do that, because again, that problem that I had just given you, how often are you really given something in moles in real life? Very rarely are you given moles. What are you actually given? You're given grams. So let's do this same problem, but I'm just going to change out, come on. I'm just going to change out the unit here. So we're going to take this out. I'm going to take this out here. And instead of having 21.2 moles, we're going to have 21.2 grams. And I want you to tell me how many grams of oxygen are contained with 21.2 grams of Ca3PO4. So I'm going to let you work on that on your own. Give you about 7 minutes. Check out on the flow chart where you're starting. You're starting out with a mass compound amount and you're trying to get to a mass element amount. All right, so in this problem, I'm gonna move back up here. So we are all good with this flow chart. So we're starting with grams of the compound, the calcium phosphate, and I wanna know how many grams of oxygen that is. So we have to go from grams of compound into moles of compound, from moles of compound into moles of element, and then from moles of element into grams of element. Hopefully you can see how this is sort of all getting stitched together. So the first thing is to go from grams of compound into moles of compound. This is probably the most work that you have to do in any step, which is to calculate that molar mass. And the molar mass of calcium phosphate, I just had a, I'm going to write it up here. We've got a molar mass of 310.18 grams per mole. So start with our given information. 21.2, and now we're doing grams of Ca3, PO4, 2. First thing I need to do is get it into moles. So for every 1 mole of Ca3, PO4, 2, this thing weighs the 310.18 grams of Ca3, PO4, 2. Okay. So here we've got molar mass of compound. Next step is to go from the moles of compound into the moles of the element. So for every 1 mole of the compound, PO4, 2, we get 8 moles of oxygen. This is the formula subscripts. So it's a 1:8 ratio. And then the last step is to figure out, I didn't want moles of oxygen, I want grams of oxygen. So the last step is to go from moles of oxygen into grams of oxygen. So for every 1 mole of oxygen, it weighs 16 grams. The moles of the element cancel, the moles of the compound cancel, and the grams of the compound cancel. So we're going grams to moles to moles to grams. That flow chart, or that gram to mole to gram, is going to come up over and over again, especially when we get into stoichiometry, which is where we use balance equations to do a similar sort of process. I ended up with 8.75 grams of oxygen. This number should always be less than the number of the compound, because the mass relationship, right, the individual amount, the mass should be less than the total mass. Any questions on this, on what we're doing with that? You got to ask me, or I'll assume you know it all. Let me just fill in here on this step. This is the molar mass of the element. Now, it's one thing that I see people do is they'll say, well, don't I need to do 8 moles because there were 8 moles of oxygen? No, we only take into account the ratios in this step here. This will be a 1 ratio. This is also a 1 ratio. Okay, so don't include the 8s or the whatever it happens to be, the subscripts are on these side wings. Okay, so we'll continue on. So that's, you can kind of think of this as the first part of the chapter. It sort of encapsulates all this. So if you are comfortable with moving around this chart, then you've got really the first part of this chapter down, right? This sort of sums it all up. The second part of the chapter, we're talking about mass percents. Okay, I feel like this is gonna seem a little bit easy. and refreshing compared to the last part. Here's the idea of mass percent. So the mass percent composition or mass percent of an element is the percentage, the element's percentage of the total mass of the compound. So if I have a formula and I say, well, what's the mass percent of oxygen? You're going to take the mass of the oxygen and divide it by the mass of the compound and multiply by 100. So not too bad. I don't want to do that one yet. No, I don't like using it as a unit. So like, let's say we have this formula here. So I've got CCl2F2. If I want to find the mass percent of chlorine, I'm going to take the mass of the chlorine, but I do need to multiply it by 2 because there are in fact 2 of them, divided by the molar mass of the entire compound, and then multiply by 100. So I want you to try this one here. So we've got C2Cl4F2, and I want to know what the mass percent of the chlorine is. Excuse me. So I'll give you a minute to try and work that out. It sort of gives you the base structure here, but I want you to plug the numbers themselves in. So let's look at this one. We've got Freon, C2Cl4F2. Don't use this for mass percent stuff. All right, this doesn't pertain to this section. I'll sort of ignore that flow chart. Oh, go away. So our formula is C2F C2Cl4F2, I believe is our freon. Yeah. Okay, so if we want to find mass percent of the chlorine, I'm going to take the mass of chlorine, which is 35.45, and I'm going to multiply it by 4 for that top value, because there's 4 of them. If it was just one chlorine, we would only have to do the mass of one chlorine. So the molar mass of this whole thing is 170. That's it. Hold on 1 second. 2, 4. Okay, something's not right there. Let me just add it up. So 35.45 times 4 plus 12.1 plus okay, I got 203.8. Can someone give me confirmation on that? That is the molar mass of that. Sometimes my adding and subtracting can be terrible. Just throw it in the chat if that's what you got. Reconfirm it. I'm not getting any confirmation from anyone, but I'm assuming I just double checked it. So that's what I got. Okay, so then we take our 35.45 and we multiply it by 4. We have 141. So most of this thing is the chlorine divided by the 203.8. And we multiply this thing by 100 to get it into a percentage. And I've got 69.6%. So over half of this thing is almost 70% of it is the chlorine. Questions on that? Let's do another one. I'll have you do it. Let's say we've got what formula do I want to use? What is the mass percent of sulfur in you got a bigger molar mass for the whole thing, Gabriella. Okay, hold on one sec. Let me write this problem down and then I'll get to that. So what is the mass percent of sulfur in copper 1 sulfide? Okay, start working on that one. Go back up here. So you got a bigger molar mass for all of them. So we had 2. So we have 2 copper or 2 carbons, 12.01 times 2 plus 35.45 times 4 plus 18.99 times 2. I got 203.8. What number did you get in there, Gabriella? Because if you got like 23.9, that's okay. If you got like 217 or 500, I would recommend recalculating it. I'd gotten 241. Yeah, I would try it out again. 35.45 times 4. Yeah, try it with 2 carbons, 4 chlorines, and two fluorines. I'm not getting 241 for that. You see what you did? Okay, perfect. Glad you could get that figured out, Gabriella. Yeah, try in this one. So what is the mass percent of sulfur in copper 1 sulfide? If you're like, ooh, well, where's the formula, Candace? Well, you have to write the correct formula. So naming and nomenclature doesn't go away. It's going to be with us for the rest of the semester. Not as heavily as the last chapter, but it's still going to be there. Okay, so in this situation, we want to figure out the mass percent of sulfur in copper 1 sulfide. So we have to be able to write a correct formula for this. Otherwise, our percentages are going to be off. So copper 1 sulfide is not telling you you have 1 copper. It's telling you that you're dealing with copper with a 1 charge. Sulfur always has a 2 minus flip-flop, so our formula needs to be Cu2S. If you just smushed copper and sulfur together, you're missing one of the coppers in the mass, the total mass, and it's going to throw the percent off. So sulfur percent is going to equal the mass of the sulfur over the mass of the Cu2S times 100. We only have 1 sulfur, so it's just going to be the 32.066 all over. We've got our copper mass, which is 63.546, but we have 2 of those because it's balanced correctly. We have 2 plus the mass of a sulfur, which we said was the 32.066. So my total mass should be 159.158. Okay. Now, if you had like 159.16, that's okay. It's close enough. We'll take our 32.066. And divide it by the 159.158 and multiply it by 100, and we should end up with 20.1%. So 20.1% of this material is coming from sulfur. So there is a practice sheet for this in your, where is it? We've got worksheet here. Yeah, there's a mass percent practice sheet that empirical formula, molar mass. I'm not going to go over any more of them, but this formula sheet has a bunch of practice and it also has the answers. So you can look at all these different formulas, can calculate what is the mass percent of these, and then it actually gives you the answers and it shows you the basic work for it. So you can tap into there if you need a little bit of extra help. So we were able to go from the Zooms. Yeah, I'll get them posted tomorrow. Usually I get them posted on Thursday because that's when my lectures end, all of my lectures for the week, and I just upload them all at the same time. So we were talking about going from the chemical formula to the mass percent. Is there a way to go from mass percent? So I could give you the mass percent. Hey, it's 55% this and 12% this, and the remaining part is this. Could I calculate a chemical formula? And the answer is yes. But it is a little bit more, it's a little more intense going from mass percent to chemical formula. This way is pretty easy. It's just, the mass of what you're trying to find divided by the mass of the compound times 100. This is going to require a few more steps. So we're going to break there because I don't want to get into this just yet. I want that to sort of be preserved as a whole. But yeah, we will stop there. If you have any questions, feel free to stay around. Otherwise, you are all done for the day, at least with this class. So go out and have fun. And I will see you next week. Make sure you're getting the labs and the homeworks done. Your test grade should be up. You should be able to see what you did, what you got wrong, and things like that. All right, bye-bye.